Hello friends, in this video we're going to discuss about Stefan Boltzmann's law and its thermodynamical proof. So before we start, please do subscribe the channel, hit the thumbs up button. Also share with your friends, inspire me to create new contents for you and help me to grow my channel. So now let's start. So the Stefan's law states that the rate of emission of radiant energy by unit area, the rate of emission of radiant by unit area of a perfectly black body is directly proportional to the fourth power of the absolute temperature, its absolute temperature. So this is the statement according to which E is equal to sigma T to the power 4. Right here, this is Stefan's constant. And its value is equal to 5.67 into 10 to the power minus 8. Right. Watt per meter square per Kelvin to the power 4. So okay, so this is the unit. Okay, so now you see, if the black body at absolute temperature T, if the black body at absolute temperature T is surrounded by another black body at absolute temperature T naught, at absolute temperature T naught, then the net rate of loss of energy per unit area of the surface is given by E is equal to sigma T to the power 4 minus T naught to the power 4. Okay, this is Stefan Boltzmann law. This is Stefan Boltzmann's law. Right. Now thermodynamical proof. So here I have considered U is the energy density of the radiation inside a uniform temperature enclosure at temperature T, suppose. Okay, and you see, suppose P be the pressure, okay, and V be the volume of the enclosure, of the enclosure right. Now first law of thermodynamics, first law of thermodynamics, according to that law, del Q is equal to du, or you can write del U plus P del V. Okay, so applying the second law, second thermodynamical relation, it's supposed to be del Q. Okay, and so here is the heat supplied, then this is change in internal energy, and this is work done, right? So this is the first law. Then applying the second thermodynamical relation, let me simply write this thermodynamical relation. Hope you know this relation, that is del Q by del V at temperature T is equal to T del P by del T volume V. Okay, so here you see we're gonna replace this del Q by this relation. Okay, then what we're gonna have, let me write that in the next page. So here you see, and let me copy the last step. So here is the last step, last relation, and here we're going to use the first law. Let me copy this one as well. Here is the first law. So now let me replace this del Q. Okay, then what we're going to have, let me write, instead of this del Q, what we are going to write, instead of del Q we're going to write this del U plus P dV. Okay, we're going to write this del U plus P del V. Okay, so hope you have understood this. So now you see, so if you simplify this, then what you will get, del U by del V plus P T is equal to T into del P by del T. Here it's going to be V. So this is simply can be written as del U by del V, and P can be taken to other side, then T into del P by del T here minus P. That's what we can write. Okay, so now you see, since V is the volume of the enclosure we have considered, then the total energy of the radiation inside the enclosure will be given by total energy, let me write it, denote it by capital U, not small u, capital U, and we have considered small u as energy density. So and volume is V, so that's going to be equal to, that's capital U, total energy going to be U into V, right? So let me take this as equation number 1, this is equation number 2, right? This is suppose equation number 2. As we have considered this small u as energy density and volume is this, so energy density into volume, that's going to give you total energy, right? Because energy density will be given by energy per unit volume, right? So that's why this total volume divided by, total energy divided by volume, that's going to give you energy density. So that's why total energy will be equal to energy density into volume, right? So hope you have understood this. Now pressure exerted. Okay, pressure exerted, I hope you know this, that pressure, hope you know this relation. pressure exerted is equal to 1 by 3 times of energy density okay. So hope you know this relation. That's why this pressure P is equal to 1 by 3 times of U. That means U by 3. Don't write capital U here. This is energy density, so not total energy. So let it be equation number 3. Okay, let it be equation number 3. Now let us differentiate equation number 2 with respect to volume V, keeping T as constant. Now let us differentiate this equation 2. Okay, let me do it on this side. Just give me a second. Okay, sorry. So let me write differentiating equation number 2 with respect to V, keeping T as constant. Then what we're gonna get? Then we're gonna get del U, this total energy U, by del V at constant temperature T is equal to, if you differentiate this with respect to V, derivative of V with respect to V, that's going to be 1 into U, that's U. This is small u, okay. On the right hand side, this is small u and this is capital U, total energy, right? So hope you have understood this. Now, so you see, let me use this, let it be equation number 4. Using 4 in 1, let me use this in 1. So here I forgot to mention this at constant temperature T. So here let me use this equation here. Then what we're gonna get using 4 in 1, what we can have, we have this small u, that's going to be equal to temperature T into del P by del T at volume V minus P. That's what we're going to get, right? So, and also this P will be replaced by this value of P using 3. Actually I should write using 4 and 3 both, using 4 and 3 in 1 and 3 in 1, then this P will be replaced by U by 3, right? U by 3. Okay, now okay, one more thing, that what should I do here? You see, also we can replace this P by this value also. Then this equation will be of this form, divided by 3. Okay, we get that, right? So now you see, if we simplify this, let me bring this one to this side. That's going to be U plus U by 3. So that's going to be 4U by 3, 4U by 3. Then on the other side, capital T by 3, del U by del T. Here is the volume V. Okay, we don't need to mention this every time, so we can simply write this one here. Okay, now what we can do, we can write this in this form. Okay, let me write this one in this form. Here you see, if we multiply both sides by 3 and if we separate the variables, del U by U is equal to, we can write 4 into del T by T, and integrating both sides, if we integrate this equation, let me write this equation. Last we have got integrating. If you integrate this, so integration of 1 by u del u, that's going to be log of u, right? Log u is equal to, and 4 into log of t, and there must be a integrating constant. Okay, let me write this one as log a because these are in log. So log a is integrating constant. Right. So in that case, what we can write, so log u, let me write it properly, log of u is equal to, it can be written as t to the power 4. I have applied this property, log m to the power n is n into log m, right? So now this is in this form, so we can write this in this form, right? Hope you have understood this. Plus log a, and you see, you know this property, log m plus log n can be written as log m into n, right? So if we use that, then log of u, we can write log of t to the power 4 into a, right? We can write that way. And if we write that way, then we can write u is equal to a into t to the power 4. Okay, and you see also the total rate of emission per unit area of the black body is proportional to the energy density. So let me copy this equation and let me take a new slide. Here you see, also the total energy total rate of let me write it properly, rate of emission per unit area of a black body is E, which is directly proportional to U. Okay, and from this relation we have got that U is directly proportional to t to the power 4. So that's why we can write E is also directly proportional to t to the power 4, right? And so we need a constant to equalize this, that is sigma, right? So where is the where sigma is the Stefan's constant? So where sigma is the Stefan's constant. So thank you for watching. See you in the next video. Okay, bye bye.